Okay, let's look into the question number 5D4. The uncertainty of the 100 centimeter cube volumetric flask. So let's show it. Okay. So there is some volumetric flask. Okay. Okay, and its volume is 100 centimeter cube, and it is accuracy or inaccuracy is 0.6 centimeter cube plus or minus uncertainty. Okay, so let me highlight this part. Okay, this is the uncertainty which is given. Calculate the maximum percentage uncertainty in the mass of NaCO3 so that the concentration of the solution is correct up to plus or minus. So let's understand quickly what is concentration. Concentration, okay, percentage, in terms of the percentage is mass divided by volume. Okay, because please remember, mass divided by volume, that is density, is some kind of a concentration. Okay, only we are going to express in terms of the percentage. Okay, simple. So now there is a division. Okay, whenever there is a division, that means there is going to be some error here, and volume is going to be, there is some uncertainty. Okay, so I'll say this is error number, not error. Let me, this one. Okay, let me write it down properly. Okay. So I'll say this is uncertainty 1. And in volume, there is uncertainty 2 percentage. And we are trying to calculate what will be the uncertainty in concentration. So this is uncertainty 3. So what logic we are applying? Okay, this logic, very, very simple one. Okay, this concept should be clear. When multiplying or dividing quantities with uncertainties, the percentage uncertainty should be added. So simple, it simply means that we have been given that a concentration should be maximum 1%. That is what is given to us, plus or minus obviously. And mass, assume that it is a X percentage, and volume already it is given as 0.6%. So how much will be X? Simple. X will be 1 minus 0.6. That is 0.4%. Simple. That means in case of measurement of mass, the permissible, okay, uncertainty is 0.4%, because already 0.6 uncertainty is there in case of volume. And we know that whenever we are either multiplying or dividing, the percentage uncertainty gets added. Simple concept. Okay. Overall permissible is 1%. Out of that, already 0.6% is because of the volume. So balance only 0.4 for the mass. Okay. Simple. So what was the two concepts? One was the concentration. Concentration means mass upon volume. Okay, or it can be volume, this molar moles also, but finally we are talking about the mass. Okay, that's all. So it is mole upon volume or mass upon volume, doesn't matter, because that is the percentage concentration. Simple. Okay, it's very, very simple one. Okay, question number 5E. The reaction of the hydroxide ion with carbon dioxide and with the hydrogen carbonate ion can be represented by equation 3 and 4. So they have given us the equation. Discuss how these equations show the difference between a Lewis base and a Bronsted-Lowry base. So let's recap. Okay, it's always a good idea to understand the definition. So what happens in case of Lewis base and what happens in case of B and L base, that is a Bronsted and Lowry. Okay, so quickly recap the definition so that the concepts will be clear. So in case of the Lewis base, lone pair donor. Okay, that is the definition of Lewis base. Lone pair donor. While in B and L, okay, Bronsted and Lowry base, it is proton H plus acceptor. This concept has to be crystal clear. Definition, okay, the clear-cut definition, okay, should be known. Then you can easily solve. So let's look into this. What bronze, okay, so first equation, OH minus plus CO2 giving HCO3 minus. Okay, so let's try to analyze what is happening in case of this. Okay, so what is happening in this case? Let's understand that in case of this, okay, it's very, very simple. Okay, so understand in case of this, let me show with the different color. Okay, OH minus, please remember that oxygen will have lone pairs. Okay, so in case of this, okay, it gives, okay, oxygen, because oxygen is having these lone pairs, so it is going to give to CO2, okay, and helping CO2 to form this. Okay, that is how we can think of. Simple. Okay, and it will basically, so there is a gifting, so it means it is the Lewis base. Okay, extraordinarily simple. And now let's talk about the second reaction, OH minus plus HCO3 minus. Now what is happening? Okay, to give H2O plus CO3 2 minus. Now what is happening? Okay, very, very simple, that, okay, HCO3 minus gives H plus, okay, it gives H plus to OH minus. So in this case, okay, OH minus hydroxyl ion is accepting the proton. So it means it is the B and L base. Straightforward. Okay, so it should be very clear. Okay, so what is happening, that you should be in a position to analyze, okay, and understand the definition. Okay, so the definitions are different, and more general definition nowadays which is accepted is of the Lewis acid and Lewis base. That is, everything is basically lone pair. Okay, that means the electrons, because finally the chemical reactions are nothing but the transfer of electron amongst the atoms. Simple. Hope this is quite clear. Okay, interesting question. 5F. Aqueous sodium hydrogen carbonate has a pH of approximately 7 at 298 Kelvin. Sketch a graph of pH against volume when 25 centimeter cube of 0.1 NaOH gradually added to 10 centimeter cube of 0.05 mole dm cube of NaHCO3. So first understand, so what we are trying to do, we are adding this NaOH, okay, and there is a NaHCO3. So what is the specialty of this? It is simple, that NaHCO3 we have already seen that it is a weak acid, and this is undoubtedly a strong base. Okay, so now we will start looking into this. Okay, so in this case it is approximately given that sodium hydrogen carbonate pH is 7. So that means initially when no sodium hydroxide was added, the pH is just a 7, almost a neutral. Okay, now understand very importantly that we have to show the equivalence point. Equivalence point. So what is mean by equivalence point? When number of moles of acid and base, they are equal. Okay, equivalent, sorry, equivalent point. So when number of moles of acid is equal to number of moles of base. Simple. Now what do we see in this case? That NaHCO3 molarity itself is half as compared to this. Okay, you can clearly see this is 0.1 while here it is 0.05. So it is double. So what is going to happen? That please remember that we have taken the acid of only 10 centimeter cube. Okay, so at what volume it would be equal, the number of moles? Simple. That means at 5, okay, 5 centimeter cube, we should get the equivalence point. Okay, that means almost the midpoint of this. Okay, so that is the logic. At this point, it is going to achieve. So this is basically, I'll say, equivalent point. An equivalent point, we have already seen what is happening. At equivalent point, since it's a weak acid and strong base titration, the pH will be higher definitely than 7. It would be around 10. Okay. So at equivalent point, number of moles of acid and number of base are equal. Okay. The pH is around 10. And after that, it is all the strong base which is going to dominate, because already the complete acid has been neutralized, titrated, and after that it is the basically the show by strong base. So what is going to happen after that? The pH is going to just shoot up and it will go up to whatever 13, 14. Okay, that's all. Very, very simple logic. Okay, so the starting point is 7. Okay. Okay, so these are the points which should come into your this one, that equivalent point, that is very important. Okay, so in this case it is at 5 centimeter cube. The reason being that a molarity or concentrations are different. Okay, the concentration of NaOH is double than that of NaHCO3, sodium hydrogen carbonate. Okay, that is one point. Then starting point, obviously the pH is 7, and then being a strong base, the final pH could be around between 12 to 14. That's all. Okay, so this is what should get captured in this titration curve, and definitely the equivalence point has to be higher than 7. Okay, we are showing it as around 10. Simple. Hope this is quite clear.